Okay, I'd like to welcome you all to the SLAC National Accelerator Laboratory in our bi-monthly public lecture. This public lecture will celebrate the fact that SLAC is in a new business. Actually, it's an old business at SLAC to produce the world's most brilliant and intense source of X-rays. But our new business is redefining what that term means. And that's the subject of this lecture, ZAP. The X-ray laser is born. We're very lucky to have with us Daniel Ratner, who is a member of the team that actually made this thing work, and he is going to explain to you how it was done. Before we start, I'd just like to tell you all that if you're interested in these things, on the last Tuesday in January, we will have another public lecture about this X-ray laser facility, describing one of the first experiments that were done there. The title of that lecture is He Spins, He Shoots, He Scores. The two-pointer is executed on a diatomic molecule which did not know what was going to happen to it, but the physicists do. And if you're curious, please come then, the last Tuesday in January. So without further ado, Daniel Ratner will tell you all about this marvelous new device.
Thank you. Is this on?
No. It's supposed to be on.
Okay, now that works? Okay. Thank you for the introduction. So welcome to SLAC, everyone. So as you just heard, the topic of tonight's lecture is going to be the X-ray laser. And of course, it's not an accident that we chose this topic. Again, we have the world's very first X-ray laser here on campus. So it's been 10 years of hard work to get here, but it's now a brand new instrument. We had our very first laser pulses in just April of this year, and the first science was done a little under 2 months ago at the beginning of October. So it's a brand new thing. It's right in your backyard. So that's why we wanted to have you here to tell you about it. So the goal of the lecture will be twofold. First, I want to tell you what an X-ray laser is and how you go about building one. And then I want to give you a little bit more in-depth about one particularly very exciting experiment that we hope to do here. But first, before we get to those things, I want to convince you that this is something worth talking about. So, Act 1 of this three-part lecture will be the wonders of the X-ray laser. But actually, before we even get to X-ray lasers, let's take another step backwards and talk about X-rays and lasers individually. So, what is an X-ray? An X-ray is just light, like the light we see. You can think of it as another color of light. And now, physicists talk about light. They have two different pictures they use. First, they have what we call a wave picture. So we talk about light being made up of a wave, and then different colors correspond to different wavelengths, so different distances between the wave peaks. So for instance, red light has a slightly longer wavelength, blue light has a slightly shorter wavelength. And in this picture, X-rays are just very, very short wavelength light. Now we have a second picture, which is the particle picture. So now instead of talking about light as a wave, we talk about light as a particle, just the way we talk about electrons and protons as particles. And now, instead of talking about wavelength, we talk about the energy of that particle. And the particles are called photons. So red light is a slightly lower energy photon. Blue light photons have somewhat more energy. And X-rays are just very, very high energy photons. About 1,000 times more energy in an X-ray photon than a visible photon. About 1,000 times shorter wavelength in an X-ray wavelength than in a visible wavelength. But I probably don't have to actually tell you what X-rays are, because I'm sure all of you are familiar with X-rays. Almost everyone in this room has probably had an X-ray taken of their body at some point. And this is not a new procedure. Here we actually have an X-ray of the discoverer of X-rays, Röntgen. This was taken over 100 years ago. He actually won the very first Nobel Prize in physics in 1901. It gives you a sense of how important X-rays are. But of course, we can do many more things than just take X-rays of our bodies. Every time you go to an airport, your luggage is X-rayed. Hopefully they don't find that. Scientists use X-rays to look at the universe. Many of you may recognize this photo. This was the X-ray that allowed scientists to figure out the double helix structure of DNA. And actually, we have a facility here, shown here, called SSRL. It's just a little bit over that hillside. And as Michael mentioned, this is one of the premier, and has been for several decades, one of the premier X-ray sources in the world. So scientists here study all sorts of fields, of course physics, but also chemistry, biology, material science, environmental science. If there's a science, they've studied it here. Even actually pioneered a technique recently that's been used to recreate images of paintings that have been overlaid by other paintings. Here, an example of Van Gogh. And in case any of you still don't believe that they're important, they've even made it onto The Simpsons, which I think is the mark of cultural acceptance. So we know what X-rays are. Now, how about lasers? Now, lasers, like I have one in my hand here, are light sources, right? I shine a little bit of red light on the screen. The question is, how does this laser differ from another light source, like the bulbs above us? And there are three main ways that are important for us today. First, lasers tend to have a single color. So this is a red laser pointer. So if you have a fancy laser pointer, it's just green light. Whereas light that comes from a light bulb has all sorts of colors. And so that's why we see it as white light, because it has red, green, blue, all the colors. And another way of saying this, because color corresponds to wavelength, is that a laser has just one wavelength in it. Secondly, lasers tend to be very bright. And this is basically the same meaning we have when we talk about a bright light source. So a laser, we talk about photons, has many more photons coming out of it than you typically expect from a regular light source. And thirdly, the light that is emitted from a laser comes out in unison. So if we talk about waves, all the waves are going up and down together at the same time. Whereas talk about light from a light bulb, the waves are all jumbled up. And in some ways, this is the most important feature, because this is really what gives us this brightness and the single color. But again, I probably don't have to tell you what a laser are, because lasers are all around us. Of course, there are laser pointers, like the one I have here, or the fancy green ones. And just to name a few of the uses, there's laser cutting, laser surgery, like LASIK, DVD players and CD players all use lasers. Telecommunications, fiber optics use lasers. There was a recent New York Times article about a group that's scanning entire cathedrals, and they're actually going to go scan all of Mount Rushmore soon, using lithography to write it onto chips. And of course, there are the mega lasers of the world. I'm sure everyone recognizes this from Star Wars. But this actually is no longer just science fiction. Just across the bay, some of you may have heard of the National Ignition Facility. This will soon be the world's most powerful the most powerful laser, not an X-ray laser, most powerful normal laser, and will be used to study fusion as an alternative energy. So we have X-rays and we have lasers. We know that X-rays are awesome. And we know that lasers are awesome. What happens when we combine them together? And so for the very first time, we have an answer for you. It is LCLS, the world's very first and only X-ray laser. So what's special about this? I want to tell you 3 reasons why it's special. So first off, it's very intense. What do we mean by intense? Well, one way to say this is that there are a lot of photons. In fact, over 1 trillion photons in a single pulse. So it's very, very bright. In fact, it's 10 billion times brighter than the current brightest X-ray source in the world. Just hugely brighter than any other X-ray source right now. Another way to say this is that there's a lot of power. Over 10 gigawatts of power. To give you some perspective, this is 5 times the amount of power that you get from a typical power plant like Diablo Canyon. Now, of course, this is not continuous power. It's not like we need a nuclear power plant just to run this thing. You only get that power for a very short amount of time. But when you do have it, it's extremely, extremely bright. And now, because I always get this question from an 80s cinephile whenever I give tours, it is also about 10 times the amount of power required to run a flux capacitor. So it's a lot of power. Okay, so we know that it's intense. The second feature of it is that it's fast. So what do we mean by fast? So here's a video to try to demonstrate this. This is actually the very first film taken of a horse galloping. And you can see, if we look at the individual stills, that at some point, the horse's hooves are all off the ground at the same time. And actually what they discovered here is that the hooves, when they're off the ground, they're tucked underneath the horse. Whereas if you see old paintings, the horses are always splayed out like this, because no one actually knew what a horse did when it galloped. And the reason they were able to discover this, was because the photographer, Edward Muybridge, was able to take a very fast photograph. And he was able to capture the horse in mid-motion. If it had been a slow photograph, this would be all smeared out. You had no idea what's going on. So it's the fact that he had such a fast photograph that lets us see this. Now, incidentally, some of you may recognize this barn. This is actually where a lot of this work was done, here on Stanford campus. So we actually have a long history of ultra-fast photography here. But we don't want to take pictures of horses with our X-ray laser. We want to take pictures of atoms. And as you might guess, atoms move a lot faster than horses. So, well, Muybridge, he did pretty well. He got about a millisecond, about a thousandth of a second per shot. We want to do a little bit better, though. We want to get down to the level of what's called a femtosecond. This is 1 part in 10 to the 15. That's 0.0001 with 15 zeros of a second. To give you some sense of this scale, a femtosecond is to a minute as a minute is to the age of the universe. So this is a very, very short amount of time. So it's intense, it's fast. The third thing, tiny. Well, that doesn't sound very impressive. But what we mean by tiny is that we can see tiny things. So in particular, we want to look at molecules. So we want to be able to see down to the atoms in the molecule. And atoms are about 0.1 billionth of a meter across. So we want to be able to see things that are this small. OK, so it's intense, it's fast, it's tiny. We have all three of these things at once. If we want to say this in superhero terms, you might say that it's super strong, it's lightning fast, and it has X-ray powers. Yes, this is the Superman of the light source world. Though, I'm not making this up. Here at SLAC, we actually have our own superhero. His name is Slacker Man. He looks like Einstein after a trip to Barry Bonds' trainer. But in seriousness, it's the fact that we have all three of these things together that makes this special. That's what allows us to do things here that have never been done before. So as you heard, you're going to hear more about this in the coming public lectures, but I just want to give you 3 quick examples. First off, we can take a picture of single molecules. And I'll actually spend the 3rd section of this lecture talking about why it's important. But for now, I just want to convey that this is going to be the first time we've ever been able to do this. So this gets a little first time ever award. Secondly, we're going to make movies of chemical reactions. So what do we mean by that? Well, we know, or some of you may remember from your high school chemistry class, if you take an oxygen atom and you take 2 hydrogen atoms, what do you get? You get water, right? We all know that you go from, take some atoms, and you end up with a molecule. But actually, we don't know what happens in between. This stage here is very, very fast. And we've never been able to have something that's intense enough, that has the resolution, and also the speed to capture it. But because we have all 3 of these at once, we will be able to take a movie of this type of process. So the first time ever, we'll be able to understand what's actually happening in between these 2 states. Again, first time ever. Oh, and again, there are many different things we can do. I just want to give one more fun example. It's called the atomic catapult. Now, probably some of you know what a catapult is. This was a medieval device for flinging boulders at castle walls to knock them down. We obviously don't want to fling boulders. We want to catapult atoms. And the way we can do this is we take a laser pulse, and we can make a bunch of highly charged atoms. They all have positive charge. And 2 particles with the same charge don't like to be next to each other. They get repelled. So if we have some little tiny particle on the outside with positive charge, it doesn't want to be next to these, it gets shot off. So this is kind of fun. We've made an atomic catapult. But it's actually not just fun. There are actually interesting applications. In particular, it could be used to study fusion and fusion as alternative energy. And again, first time that we've ever been able to do this. So again, there are many other applications, but hopefully this is giving you a sense of how useful this is. And so now I want to switch over and talk about how we actually build one of these. So say you want to do it yourself, build your own X-ray laser. What do you have to do? So first off, let's talk about how a normal laser works, like this one here in my hand. You might ask, no, why can't you have an X-ray laser pointer? So what's in this guy? Well, it has an energy source, so there's just some batteries in here. There's something in it that makes the light, because there's light coming out, right? And then there's some process here that makes it all work together. So why can't I have an X-ray laser pointer? Why can't I just have something like this, and every time I think I might have broken a bone, just point it at my hand? But the biggest problem is that there's no easy X-ray light source. Now, the way that you make light in a conventional laser, you use what are called bound electrons. So what we mean by that is we have this atom here, and there are electrons that are going around the nucleus, but they're bound to this atom. They can't escape. And it turns out that the light that you get from these bound electrons just isn't useful. You can get X-rays, but they're not useful X-rays. So we need a different system. Bound ones don't work, so maybe free electrons will work, electrons that are not bound to any atom. And then we need some kind of laser that will work with these free electrons. So basically, a free electron laser. Now, luckily, we don't have to invent this. It already exists. It's called the free electron laser. And it was invented by John Mady in 1971 here on Stanford campus. It was actually, the first one was built here in 1977. And not an X-ray laser. This is just a normal light laser, like the light that comes out of this one, but built with this special free electron laser. The only thing I want to point out here is that all the way back in 1971, John Mady actually knew in this paper that it could be used to build an X-ray laser. So we have a long history here of this at SLAC. Now, how do we actually go about building one? Well, it's going to have the same basic ingredients that this X-ray laser pointer does. I need to have some energy source, but in this case, instead of being a battery, it's going to be a particle accelerator. I need some X-ray source. It actually turns out that once I've accelerated these particles, we're going to use electrons. Just with magnets, we can get X-rays out. And then I need some sort of laser magic to combine it all together. And this is what the free electron laser is. But I actually need one final ingredient, and that is lots of accelerator expertise. Because it turns out this is a very hard thing to do. And the first and fourth reason explain why we have built the first one. We have the world's biggest and best linear accelerator, and we also have some of the top accelerator physicists in the world. And so that's how we're able to do this before anyone else in the world. So I want to go through all of these sources, all these items individually. But first, I'm going to give you a one-page detour and make you all special relativity experts. So you all know Einstein, I'm sure. He gave us two rules. The first one, the ultimate speed limit, which is the speed of light, right? Nothing can go faster than the speed of light. So here we push these electrons very fast. They go 99.999% the speed of light, but they can never go faster than the speed of light. But it turns out, second rule, funny things happen when we start going the speed of light. In particular, there's one that we're interested in, and that's that fast objects appear smaller. So if I'm sitting in this yellow car, and I go zipping in front of you, even though I think that I'm in a normal car, you'll see me as being in some sort of squished circus car. And this is not a small effect. At LCLS, you'll see these electrons, at the speed of the electrons, you would see this car squished by 20,000-fold. So you would see my car having the width of a piece of paper. So this is sort of a remarkable effect that Einstein told us about. And then there's one third corollary to this, which is that all motion is relative. So what do we mean by that? Well, you're here, say we're out in space, and you see me zip by in my car. Because of what Einstein told us, you see my car shrunk down to the width of a piece of paper. But from my perspective, I'm just sitting there in my car, and it's you who's zipping by me at this close to the speed of light in the opposite direction. So I actually think I'm still normal, and you zipping the other direction and have been squished down to the size of a piece of paper. And so what does that mean for us? That means even though we think that these electrons are zipping by at close to the speed of light, they actually think that we're zipping by them in the opposite direction at close to the speed of light. So they actually see the lab shrunk down. Okay, now you're all special relativity experts. Now we can explain all of these items. First off, the energy source. So our energy source is going to be an accelerator. We want to make high energy electrons. So how can we make a high energy electron? So the electron, I'm going to use this shorthand, the E minus for electron. And the minus is there because electrons have negative charge. So negative charges like to go to positive charges. So if I put this next across a battery, it'll want to zip to the positive side of the battery, and it'll gain energy. But it doesn't gain very much energy. So what can I do? Well, I can put lots of batteries one after another. Now, I'm doing better. Now I have 15 times as much energy. The problem is, if I want to get to the energies that we need for LCLS, I would need 15 billion AA batteries. Now, it's not very practical. I don't think the safety people would like this. So we needed another solution. And the answer is we accelerate the electrons on a radiation wave. So you can think of this as a surfer. if the surfer stays on the right part of the wave, he's always pushed forward. And it's the same for the electrons. As long as the electrons stay on the right part of this radiation wave, they'll always be pushed forward. And the things that do this are called klystrons. They're just basically really big microwave ovens. But I point them out merely because they were also invented here at Stanford. So again, we have a long history of accelerator physics here. OK, so we can put all of these together. And this here is the linear accelerator. It gets very, very high energy electrons, up to the equivalent of 50 billion AA batteries. And there is a lot of energy in this. Remember, I told you we had 10 gigawatts in the X-rays? Well, that's less than 0.1% of the energy that's in the electrons. So even though we actually don't even need this full 50 billion, we actually only use the final third of the LINAC. So we use 1 kilometer of the 3-kilometer linear accelerator. And finally, I want to just point out again, this is the only place in the world where this is possible. Some of you may have heard of CERN, which has the Large Hadron Collider. That's the largest accelerator in the world, but it's a circular accelerator. It's a different kind of accelerator, and you can't build an X-ray laser with it. We still have the world's biggest and best linear accelerator. OK, so we have our energy source. Now we have these high-energy electrons. How are we going to get X-rays out of them? Turns out that if you bend an electron, it radiates energy. So for instance, this is how radio towers work. The electrons go back and forth, and they give off radio waves. It's also how X-ray sources, like our X-ray source here, SSRL, that's also how that works. Although at modern X-ray sources, we use these things called undulators. And they're basically just a series of magnets. So we have magnets pointing up, down, and as the electron goes through it, first it gets pushed up, then it gets pushed down by the magnet, then up, and as it wiggles back and forth, it gives off X-rays. And here's a picture of the LCLS undulator, and actually each of these teeth here is, it corresponds to one of these magnets. OK, but the question you might ask here is, if electrons, when they're bent, radiate X-rays, why don't we get fried every time we go by a radio tower? Or conversely, you might ask, if they don't get X-rays at radio towers, why are we able to somehow magically get X-rays here with the undulator? And this is not a silly question. It's actually remarkable that we get X-rays, because the X-rays are 200 million-fold smaller than the undulator period. So we start with this 1-inch magnet, and I'm telling you that somehow we get these things that are 0.1 billionth of a meter across. This doesn't make sense. That's like saying that I can make a normal-sized painting with a paintbrush the size of the Earth. How do I go from something so huge to make something so small? And we have two explanations for this. First off, we have Einstein again. He told us that when objects go fast, they look smaller. So we have electrons. The accelerator makes very fast electrons. And to the electron, because of this, to the electron, the undulator is moving fast. The electron actually thinks that's the undulator that's shrunk. So even though we see this normal size 1-inch undulator in our lab, each of these being 1 inch, the electrons see something tiny. They actually see that period as about a millionth of a meter. So that's pretty good. We're down to a millionth of a meter. But we have to get down to less than a billionth of a meter. So we need one more piece. And that's that this light that's about a millionth of a meter is coming off of a moving electron. But we're not moving. We're stationary in the lab. So what do we see? And this is actually an effect that you've probably heard in everyday life. Play a little audio sound. So some of you may have heard this before. What you're hearing is we start with a, you hear the siren. It starts at one pitch, and then it goes down to a lower pitch. So as a siren is coming at you, you hear a higher pitch. And as it's going by you, you hear a lower pitch. You may have heard this as a cop or ambulance goes by you. So again, the high pitch goes down to the low pitch. This is called the Doppler shift. So what's happening here? Well, so suppose we have an ambulance that's making this sound wave. The sound wave is going to expand out. But as the sound wave is expanding out, the ambulance is moving forward. So when it gives the next sound wave, it's going to be closer to the front than to the back. As I keep going forward, I'm always giving off my sound waves closer to the front than to the back. So if I'm in front of this, as the ambulance is coming towards me, I hear these sound waves that are very close together. I hear a high pitch. And then as the ambulance is going away from me, I'm standing over here, I hear these very long wavelength, low pitch sound coming at me. And that's why we hear the change in the pitch. Well, the same thing happens for the electrons. The electrons are producing this long wavelength light, but as they're zipping at, I see them coming at me, so I'm on this side. I see it all compressed to very short wavelengths. What do I see? I see X-rays. So this is the principle. This is how we're able to make X-rays in a lab. Okay, so we have our high energy electrons. We have our X-ray source. Now we need something to put them together. So how are we going to combine these with some sort of laser magic to actually make a laser? And just to remind you, what do we need? We need to have single color, which is the same thing as saying a single wavelength. And we also want it to have lots of power. And we're going to get this because they're going to be X-rays are all going to be giving off in unison. So we'll tackle these one at a time. First off, why do we see a single wavelength? So another way to say this is, why is one wavelength more special than all the other wavelengths? So let me give you an analogy here. Suppose I'm back in my yellow car, and I'm driving down some windy country road. But as I start going down that road, there's a speedy red Tesla next to me. And it's going to be going down a highway. So this Tesla, because it's a Tesla, can go faster than my dinky yellow car, and it's going to be going straighter, so it's taking a shorter path. So as we start driving, the Tesla is going to get ahead of me. And when I come back to the road, I'll see that the Tesla has gone ahead of me, right? This makes sense. I keep going, the Tesla keeps on getting further ahead of me. That's all as we expect. But now suppose we're a couple years in the future, the economy has recovered, and Teslas are as common as Priuses are today in Palo Alto. They litter the roadway. But the same thing happens, they're still speedy. So as we start going, the Tesla is still going to slip ahead of me. But if these Teslas are spaced just right, when I come back to the road, there'll be another Tesla right next to me. So I'll look over, I'm still next to the Tesla. We keep going. Of course, that Tesla's going to keep getting ahead of me. When I come back to the road, I'm next to another Tesla. If all I care about in life is being next to a Tesla, then as far as I'm concerned, I'm actually keeping pace, right? Well, such is the life of an electron. Light moves straight, and of course it goes the speed of light. Electrons, by definition, must move slower, and they take a bending path. So if I'm an electron and I'm sitting next to this X-ray, after I go down my path, the X-ray has gotten ahead of me. But if these X-rays are spaced at just the right distance, there'll be another identical X-ray right there. And as an electron, I don't care. An X-ray is an X-ray. As long as I'm right next to it, I'm happy. So as long as these X-rays are spaced at this special wavelength, then this electron can keep on interacting with the X-rays. And this will be the special laser wavelength that we see at the end. Okay, so we have the one wavelength, but we still need lots of power. And to get lots of power, we're going to get our photons in unison. So how does this happen? So the main distinction between a standard X-ray source and our X-ray laser is this. In the standard X-ray source, we start with electrons, and the electrons produce X-rays and destroy. We use the X-rays. In a laser, the electrons produce the X-rays, but the X-rays then act back on the electrons. So we have this sort of feedback process. And what happens is the X-rays are able to change the electron energy. And to describe this, you can think of, if you're pushing a child, so I push a child on a swing. If the child is swinging away from me as I push the child, then what happens? The child swings higher, right? I've given the child more energy, and the child will swing higher. But if the child is coming at me as I'm pushing, then I'm slowing the child down, so the child is losing energy. And this is the same thing that happens with the X-rays and the electrons. If the X-ray is pointing in the direction the electron is going, it gains energy. If it's pointing in the opposite direction, then it loses energy. And by this process, the X-rays are able to push the electrons into bunches. So here we have a simulation. The white dots all represent electrons. And we start with this soup of electrons. And through this process, the X-rays push the electrons around. And by the end of the process, we're left with this nice bunching of the electrons. So we start with this just soup of electrons, and we end up with the electrons all spaced at this exact X-ray wavelength. So what does that mean that they're all bunched together? Well, that means that the electrons are giving off the photons in unison. And just the way my mother always told my brother and me that if we cooperated, we would be stronger than both of us individually, the same is true of the electrons, many-fold over. It actually turns out that these electrons produce 1,000,000 times as many photons as they would if they were all acting separately, selfishly. So the fact that they're in unison is what gives us this super high power. Now, of course, this process takes some time. And so this is a picture looking down the hall where all of this happens. We have the undulators on the left here. And you can see there's a tiny little dot there. That's actually a person, to give you some sense of the scale. So this whole thing is longer than a football field, takes over 3,000 sets of magnets, to give you some sense of the magnitude of this project. So now putting it all together, so we start with the accelerator, the final third of the accelerator. This is 1 kilometer here. This is 280 going over it. Then this laser process I just described happens under a hillside here. And then we have some experimental halls at the end where we actually use the X-rays. And then this is where we are in this building. We're at the end of this little building to give you some sense of the scale of this whole project. And we actually have a nice simulation that shows exactly what's happening. So first off, we have to start with the accelerator. The accelerator is 40 feet underground. But before we can accelerate the electrons, we have to produce the electrons. And this we actually do with a conventional laser. Although it's a pretty special laser, but it's a conventional visible laser. So we have laser pulses that come down, they hit a chunk of copper, and they knock off bunches of electrons. So we then capture those electrons, as shown in blue, and we're going to capture these electrons, and we're going to send them down to the accelerator. Now, before we can accelerate them, we have some nasty long bunch of electrons. We have to compress it into a nice tight bunch first, and that's shown here. It's what's called a bunch compressor. And it's a little wiggle that forces the long bunch into a nice tight bunch. Okay, so now we're good. We're off to the races, accelerating towards the speed of light, closer and closer to the speed of light. And actually, before we can really get there, we have to compress again. And this second compression stage, this is what really gives us these ultra-short pulses, down to a femtosecond. Once we've done that, then we can really accelerate them, going down this full kilometer. It takes us a little while, just even in this simulation, to do it. It takes the electrons about a millionth of a second. Then we have some diagnostics. It turns out it's actually very difficult to build one of these. You really have to know your electron bunch very well. We spent 3 years working with these diagnostics and other diagnostics to understand this electron before we could even start making the X-rays. Then finally, we're ready to make the X-rays. So here we are in the undulator hall. Each of these is made up of many, many magnets. So all of these ridges are magnets. And as we go along, this is the process that I just described to you. The electrons bend up and down. As they're bending up and down, because they're wiggling, they give off X-rays. That's shown here in yellow. And then because it's this special X-ray laser, those X-rays then act back on the electrons. So we have this feedback. X-rays make electrons. Electrons act back on X-rays. And we start bunching the electrons into slices. And so by the end, when we're done, we have these nice slices of electrons and super, super high power. So that's the X-ray process. We go through all 130 meters of these undulators, these magnets. Once we're done with that, actually the only reason we need the electrons is to produce the X-rays. So at this point, we're done with the electrons, and we can get rid of them. So we actually bend them down. We send them into sort of an electron garbage can in the Earth. They're happy. Electron heaven, I should say. And then we just take off the X-rays into the experimental hall. We actually have a suite of experimental halls. Each one has a different type of instrument for a different type of science. Currently, we're just using this first one to do science because we're in the early stages. But in about a year's time, all of these will be commissioned, and we'll be doing a wide range of sciences here. Okay. So now we have a sense of, before I move on to the experiment, I want to give you a little bit of sense of how difficult this is. I'll give you some fun facts about the construction process. So first off, the electrons. The electrons have over 10,000 amps of current. So this is between about 100 and 1,000 times the amount of current that typical homes can handle. It's a lot of current. But it's not just that. It's also accelerated by very, very high voltage, the equivalent of 15 billion volts. So, of course, your home has about 100 volts. Even these high voltage transport lines are about 100,000 times less voltage than this. So very, very high voltage. And so we have high current, we have high voltage. You combine those together, you get very, very high power, over 100 terawatts of power. Now again, it's only for a short amount of time. We're not using the entire world's energy supply to do this. But in that time, we have very, very high amount of power. That's the equivalent of 1 trillion light bulbs. But we're not done. We then take this very high energy electron beam, and we have to put it through a pipe that's the size of a straw, but longer than a football field, We're doing this in a hall, this undulator hall where the temperature is controlled across the entire football field down to 1/4 of a degree. And the magnets in this hall are so sensitive they have to be fixed within the thickness of a human hair, and they have to even be shielded from the Earth's magnetic field. Even the civil construction was difficult. 5 million cubic feet of dirt removed, 120 concrete trucks just for a single experimental hall. The undulators in that hall have to be aligned so well, they actually have to be aligned flatter than the surface of the Earth. Even the curvature of the Earth is too much for them. And then when we finally produce these X-rays, the components that interact with the X-rays have to be so strong they're actually made of boron carbide, which is a primary material in tank armor. So, gives you some sense of how strong they are. And then finally, of course, putting all the pieces together. The order of 100 people working on this project. I just want to highlight 3 of them here. First, on the left, John Gallagher, our fearless leader, being recognized for this achievement. And then on the right, Paul Emma and Dave Dowell, who were recognized by the International Free Electron Laser community this year with the FEL Prize for their contributions to this field, recognizing how important this achievement was. Okay, so we've made the X-ray laser. Now what are we going to do with it? Again, there are many, many different things that you can do with an X-ray laser. I only have time now to tell you about one of them. So I'm going to tell you a little story about probably the one that was the biggest reason for why people wanted these to be built. And to do so, I'm going to tell you a little story about biology. So first we have to talk about proteins in the body. What are proteins? We say proteins are what make the body go around. They do everything in our body. Hair, muscles, nails. But more than that, they're also the chemical processes. Proteins are really what govern and control all the chemical processes in our body. So people often say that DNA is the blueprint of the human. But DNA is really there just to make RNA, and the RNA is mostly there just to make protein. So in some sense, protein is really what makes us who we are. So let me give you one example of a protein. It's the same one I showed earlier. It's called RNA polymerase II. And actually, Roger Kornberg won the Nobel Prize in 2006 for showing what its purpose is. And what is its purpose? Well, it is actually the protein that takes DNA and turns it into RNA. So it's sort of a metaprotein. It's the protein that helps make more protein. And he actually did a lot of this work here at Stanford, at SSRL. So why was it important for him to come here to find out what this structure was? And the reason is the structure of a protein is what determines its function. If you know the structure, then you can see, well, the DNA fits in here, and there's this thing that comes here, and it zips like this. It's all determined by what the shape of this protein is. So this structure is very important. Let me give you another example to try to convince you how important the structure is. Some of you may have heard of these drugs, Gleevec and Tasigna. They're anti-leukemia drugs, and very, very successful anti-leukemia drugs. Gleevec is actually being used by 200,000 people worldwide. Actually, it was just featured in the New York Times also a few weeks ago. And the way that this works is that we have this cancer protein here, and the cancer protein wants to interact with this green blob to make more cancer cells. And so the drug, this is its generic name, imatinib, basically just sits in the hole where the green blob wants to go. And because it's sitting there, the green blob can't go there. And if the green blob can't go there, the tumor cell can't proliferate. So in a little more detail, this green here is the cancer cell protein, and Gleevec, this little drug, sits in this groove and stops the protein from working. And that's great, it works very well. It's treated many people. But the problem is sometimes you get mutations. And when this cell mutates, its shape changes. And when its shape changes, this Gleevec can no longer fit in there. So there are actually a number of mutations, and once you get a mutation, then patients no longer respond to Gleevec. So the scientists at Novartis, which is actually where they made this first, also made Gleevec, said they looked at this and they had this structure. They say, well, Gleevec fits in here pretty well, but it could fit better if you could move this atom over here, or move this atom over here, particularly if you get this mutation. We could design a better drug. And that's actually what they did. They made this new drug called Tasigna, and you can see it looks almost exactly like Gleevec, but it's just a little bit different. Some of the, some atoms down here that weren't there. They literally designed a new molecule that fit into this gap better than the old molecule. This is called rational design. So you're using this structure to actually invent a new molecule for your use. And this Tasigna, it's been around for just a few years now, but it's also very successful. It treats almost all of the mutations for which Gleevec no longer works. So this is a very promising approach to drug design, rational design. And so the only way it works is that we have the structure. So somehow we have to get a structure of this protein. We say structure, basically a photograph of this protein. So how can we take a photo of a protein? So here's the process in 4 not-so-easy steps. First off, we have to get the protein. So we have to figure out what protein we're interested in, isolate it, make a lot of copies of it. That's some lab work. Then we want to make it into a crystal. That's why it's called crystallography. So by crystal, I mean we want to make a rigid structure of it. So lots of these molecules all arranged in some very rigid structure. Once we have this crystal, we can take it to an X-ray source, for instance, SSRL, and drop it in the X-rays. You drop it in the X-rays, you capture some data. That's shown here. And then finally, we have a computer that looks at this data and reconstructs the molecule. Now, it turns out all of these are hard. Of course, all the biologists here will tell you how hard it is to make these proteins. It's hard to build something like SSRL. This step was very difficult for many years. People have worked on. But it turns out, by far, the most difficult part of this process is this one here, crystallizing the protein. This is really the bottleneck. The question is, can we avoid this step? So how do we take a molecular photograph? We say there's sort of 2 ways we can do this. Now with crystallography, what we do is we take just a few photons, and we shine it on our crystal, and that's how we get our picture. But alternatively, we could take a lot of photons, and then just look at a few molecules to get a picture. So another way to say this is, I can either take jumbled light and look at very ordered molecules, or I can take nicely ordered light, and then I don't have to worry about having ordered molecules. I can look at jumbled molecules. So if I can't do this, if I can't make a crystal, then I have to resort to this path down here. But no one's ever been able to do this before with X-rays. So that's why this is the very first time that we've been able to do this. Now, this is not a trivial point. This is not just like the biologists are lazy and they don't want to go through this process of making crystals. You can actually only crystallize about half the proteins in the human body. And if it was split down like this, that wouldn't be a problem. You'd just look at the other half of the body. But of course, not the way it works. It's actually worse than that. Actually, many of the most interesting proteins that we want to look at can't be crystallized. In particular, membrane proteins. So the cell membrane, that's what separates the inside of the cell from the outside of the cell. And so drugs have to interact through it, and communications, very interesting biology happens there. And these guys don't like to be in water. They're very hard to crystallize. We don't know what most of these structures are, and they're very important for medicine and biology. So we really want a way to get these crystals, these protein structures. And now, for the first time, we have a way. And so here's a little video. Yes. So what we're going to do is we're going to drop molecules into our X-ray beam. And so we're only looking at one molecule at a time, but we actually have to use lots of identical copies. But so each time we drop a molecule in, hit it with X-rays, get an image. Molecule, hit X-rays, get an image. And then we can reconstruct all these images to make our protein. And so then you say, well, so what? You still had to use lots of copies. But this time, I didn't care about how they were ordered. So if I can't crystallize the protein, I can still make lots of copies of them. I just drop them in one at a time. And in the end, I get this protein structure. So this is a very exciting development for medicine and for biology. To give you some sense of how important this is, about half of the work that's done at SSRL is protein crystallography. So this is a huge amount of science to be done here, and now we have an opportunity to look at the other half of the human body. Okay, so that's it. I've given you a little bit of a taste of the science here. I just want to make one final point, which is that the X-ray laser here is in such a new regime in brightness. It's 10 billion times brighter than the brightest source in the world. We get the fastest, shortest pulses in the world. We get them at these very high energy photons, very short wavelength. Putting all of this together, we're in such a new regime that probably we haven't even come up with the biggest reward yet. Probably no one's even thought of this. So I want to encourage you to come back in the next months and years to hear about the science we're doing here. It's going to be a very exciting time for SLAC and for X-ray science. So thanks for listening, and please come back in the future to hear more.
Okay, we have time for questions, so please. Sir?
You mentioned the electron heaven. What happens to the X-rays that get done?
Oh, so the X-rays then go on to these experimental hutches where they're used to do science. And then, yeah, there's the equivalent of X-ray heaven there. You have a stop, something that's going to absorb all the X-rays because you don't want them going into the next hutch, mostly for safety reasons. So yeah, you have materials that absorb all the X-rays. So if anyone didn't hear the question, it was, what's the equivalent of X-ray heaven? We have electron heaven. So there's also an X-ray heaven.
Please, anyone?
Yeah.
What is the special wavelength in meters?
So it's from about a billionth of a meter to about 1/10 billionth of a meter. So that's a nanometer is 1 billionth of a meter, and then there's a special name for the level that's 0.1 billionth of a meter. It's called an angstrom, and the reason it has a special name is that's a very interesting length scale because that's the length scale of atoms, and that's why we've really targeted that length scale. Now, incidentally, this has actually been such a successful project. Even by the time that we got to the first user experiments this fall, we'd already gotten beyond the specs. And so we're actually working on getting to even shorter wavelengths. We've measured down to less than a billionth of a meter, and hopefully in this winter we'll down to just a fraction of an angstrom. So very short distances.
Please.
How do you decide which experiments?
So the question is, how do we decide which experiments? There's actually someone here, I think, who decides which experiments. There's a you can ask him. If anyone wants to do an experiment. No, actually, there's a proposal process. You submit a proposal like you do for grants, and there are groups that review all the proposals and then decide which ones are best. And actually, a lot of especially at this stage, because this is the only one in the world, each experiment takes about a week. Most of them so far have been big collaborations between lots of different groups to work on the experiments.
Please, up there. No,
Behind,
you.
yeah. You, the young
Yes.
one.
Fellow
You,
in the
yes.
future.
Yes, atoms are actually made up of, so atoms are made up of protons and neutrons and electrons. And it actually turns out that protons and neutrons are themselves made up of other particles. Some of you may have heard of quarks. In fact, quarks were discovered here at SLAC. That's one of the Nobel Prizes that was awarded for work here at SLAC. But that's too small for us to get into. Unfortunately, we can't look at those.
Sir.
So instead of getting rid of the electrons that you've used to get the X-rays, wouldn't it be better to use them in other experiments?
Okay, so the question was, instead of getting rid of the electrons, wouldn't it be better to use them in experiments? That is a very good question. People actually are interested in using those electrons to do experiments. There was one slight problem, is that ideally the electrons would be in front of the X-rays, but of course the electrons are going slower than the X-rays. And for practical reasons, right now we're just getting rid of them. But yeah, that's a very good question. People are definitely interested in using those electrons. In particular, it'd be nice to have what we call pump probe experiments, where first you hit them with the electrons, and then you hit them with the X-rays, and you can manipulate it with the electrons, and then you see what happens when the X-rays get to them. So yes, in an ideal world, we would do that.
Actually, can I comment on this?
Yeah.
There's a technology out there that's not being worked on here, but I think at Cornell and other places, called a recirculating LINAC, where you use the electrons and then you slow them down, you get back the energy, and then you try and re-accelerate them again. That's a future technology, though. Eventually, we'll get there.
Yes, right, and I should say that technology actually has been used in Russia for free electron lasers, but not on this scale. It's hard to do that at this energy scale, so that's a young technology.
Sir.
Yeah. Yes.
Yes. You can do it on a nice desktop. Repeat the question.
So, sorry. The question was, how much computing power does it take to go from that X-ray information to the final picture of the molecule? And the answer is not a ridiculous amount. You can do it on a nice desktop. Actually, the simulation that I showed of the electrons moving around, that kind of thing, that full three-dimensional simulation takes a huge amount of computing power. That simulation I showed is actually a real simulation that we use to study our experiment, and then we actually use big clusters running sort of on a day time frame. Oh, yeah, okay.
And that was a very fascinating thing. It took them a really long time using crystallography to be able to get that information. How much quicker will this process be?
Right. So the question was, Roger Kornberg, when he did it, it took him, I think, on the order of a decade or something like that to get that, which he was able to do because he was already famous and he could just burn through his graduate students. So graduate students don't like this approach. The idea here is that you just drop them. You don't have to do that step. Once you've made the protein, and people have known about RNA polymerase. Actually, my father worked on it. He's a biologist. He worked on it 4 decades ago. People have known about it for a long time. Once you have the protein, you just drop it in and go. I mean, it's a hard experiment to do, but days to do it instead of years.
Okay, sir in the green shirt.
What are you doing with the rest of the accelerator that we're not using now?
So the question was, what are we doing with the rest of the accelerator that we're not using? That's actually just being commissioned right now for a new sort of set of experiments called FACET that's going to be studying new ways of accelerating electrons. So we want to be able to get to ever higher energies. It takes us 3 kilometers to get this energy, but we want to get to hundreds, thousands of times this energy, and we can't build an accelerator that's 1,000 kilometers long, obviously. So this is to study new ways. Actually, we have someone working on it in the back doing laser acceleration, plasma acceleration, and particularly there they'll be studying plasma acceleration. So ways of, they actually did an experiment here before we did LCLS. They actually doubled the energy of the electron beam here. It took 3 kilometers to do the first 50 billion volts, and I think it was a meter to do the next 40 billion volts. So that's the kind of technology that they'll be studying.
Okay. Sir.
The kid in the, oh, yes, you. How do we actually do what, sorry? Well, so we're not destroying them. We're actually, they recombine with positive charges. So they're, right here they're free electrons, and then at the end they become bound electrons again.
So what happens to the samples that the X-ray goes?
Yeah.
Destroyed or damaged?
So the question is, what happens to the samples when they go through the X-rays? This is an excellent question. This is the crux of why it's going to be a very difficult experiment. Now, if you hit a little biological molecule with 10 gigawatts of power, you can imagine that's not going to be a living molecule. It's destroyed, and it's destroyed in a time scale that's something like, so a femtosecond is this 10 to the minus 15th of a second. No one knows. It could be 1 femtosecond. People guess sort of 10 to 50 femtoseconds, and no one's been able to do these experiments before. So that's something we're interested in. I believe there's an experiment going on right now looking at clusters of atoms and seeing what happens to them. So that's a very interesting question. Once we figure that out, that'll tell us how we can make this experiment
It's
work.
got to be slow because the atoms are heavy.
So yeah, so actually the atoms take a long time to move away. But it turns out when you're doing this X-ray crystallography, you're really looking at the electrons. And the electrons all get knocked off and very quickly.
So a follow-up is, at the beginning you said that you wanted to make a movie of chemical reactions.
Yeah.
So is it going to actually impede the chemical reaction you're trying to record if it's destroying the sample as it's recording it?
So you can't actually.
I think you better repeat this question.
Okay, oh, sorry. Okay, so sorry. Then the next question was, so we know it destroys the molecule. If you're trying to look at a chemical reaction, when you look at the molecule, aren't you destroying that molecule? How can you actually watch this chemical reaction? So the answer is, you're not actually just watching one molecule go through this whole reaction. What you do is you repeat this many, many times. So you start the process with a molecule, and then you take a picture at a certain time. Then you put in another identical molecule, start the process, wait a little longer, take another photo. So you're actually, it's like making a movie, but with, you take George Clooney, you make a movie, but you end up destroying George Clooney with every shot, and you get another George Clooney, and you go a little bit further in the movie, and then you assemble it all at the end.
Okay, please.
Are there things that you can do with the X-ray lasers other than just essentially take pictures?
So you need to somehow interact with them, and then you need to somehow see the, wait, let me ask this differently. So sorry, the question was, can you do anything other than take pictures with them? And the answer is yes. So as far as I know, the two main things that you can do are you hit it with the X-rays and you look at, so you can look at X-rays that come off, you can look at other light that comes off, and you can look at the things that come off. So you can right now actually all the experiments that we're doing are knocking off electrons and knocking off atoms. And you look at, so you blow it up and you see the electrons and atoms that come off. Actually, I got this slide just today. So there's actually actual data that was taken just a few weeks ago. This is some of the very first data that was taken with an X-ray laser. And the details of the experiment to go through, basically they're forcing all these molecules to line up. So when they're lined up, that's up here. When they're all horizontal, that's down here. But they actually did this not by looking at the X-rays, but by looking at the atoms as they shoot off. They see which direction the atoms shoot off. So some of the very first X-ray science ever done with an X-ray laser.
Okay, way up there.
As a follow-up on the previous question, when talking about the factor, how easy it will be to convert this into a high-powered X-ray?
Wait, sorry, say it. When the aliens attack. Thank you. So, as a matter of fact, actually, the U.S. government got to this before you. One of the original uses was they wanted to use these free electron lasers as part of Star Wars. But it turns out, well, not with X-rays, just with normal lasers. Turns out that doesn't work very well. So you cannot attack aliens with an X-ray laser. The big problem is that the X-rays end up ionizing the atmosphere as it goes to the atmosphere, and then that absorbs all the energy. So you need a tube to your alien. The alien would have to hold the tube, and then you could shoot him with it. You need a cooperative alien.
Okay.
Very small aliens, yeah.
Let's take just a couple more questions. Any young members?
Yeah, we have one right here.
Want to ask a question?
Yeah.
Would the X-ray laser be kind of dangerous then? Because I know a regular X-ray isn't the best for you. And you said it was a lot more powerful than a regular X-ray.
Yes.
So if you got under your skin, it could seriously.
Yeah, the question was, is this dangerous? Because we know that X-rays are not good. You don't want to be sitting in an X-ray machine for a long amount of time, and this is much more powerful. No one is going to be going into this X-ray beam. There are lots of interlocks. If you open any doors, everything shuts off. No one is getting anywhere close to the X-ray beam. It's being only used to study, so it can still have medical applications because it's telling us about science, about medicine, but no one is going to be looking for broken bones by sticking their hand in the X-ray laser. Yes?
You said that in the room with all the magnets that temperature was really, really, really controlled.
Yeah.
Nobody's allowed there, right?
So no one is allowed in there while, so the question was, the temperature is very well controlled in this undulator hall. Does that mean no one is allowed in? When it's not operational, you actually can go in there. There are shields on the side to try to keep as much air in as possible, and you close the door really quickly. But no one is allowed in there when the machine is on because the laser actually travels right down the middle. But there's a lot of other radiation going out at all angles. So you don't want to be in that hall while the electrons are going through it.
So one more.
One more.
please.
The question was, if we go to higher energy, would we be able to build a gamma ray laser? Going to higher, there's potential to get to higher energy photons. I don't know about gamma rays. Where's Jerong? As far as I know, there's no way you can get to gamma rays, right? We think not. Yeah. There's a long way, many orders of magnitude still to go. There are other techniques. Maybe if you, at some point, people are talking about using, instead of using a magnet as your undulator, you can actually use a laser. So then you start out with I'm talking about compressing this undulator, but if your undulator is already just a millionth of a meter, then you get to very short wavelengths. So yeah, people are looking into that kind of thing. I don't think there are stuff that you can do with the gamma ray laser, but because this is an interesting length scale, because it's the length scale of atoms, There's actually more interest at this 0.1 angstrom, I think, than at gamma rays. Gamma rays just tend to go through everything. But if we build one, I'm sure people will come up with things to do with it. So.
Okay, so I think that's the end of the public questions, but Daniel will be around for a while down here. Several of us others wearing these silly hats know something about this, and you can ask us the questions. If we don't know the answers, we'll send you to Daniel. There's another fellow in a silly hat up there. So let's just thank Daniel again, and thank you all very much.
Thanks for coming.
Good night.